King minus man plus woman equals queen. Let that sit for a second. That's an equation, not a metaphor, not a poem. An equation where the inputs are words and the output is another word that makes perfect sense. A machine solved this with no dictionary, no grammar rules, no human telling it what king means or what gender is. It just read text, billions of sentences. And somewhere in all of that, it learned that meaning has a shape. That shape is called an embedding. And by the end of this video, you'll understand exactly how it works, well enough to explain it to someone else. You'll see why every major AI breakthrough of the last decade depends on it. And you'll never look at a search engine, a recommendation, or a language model the same way again. Start with a simple question. How do you feed a word into a computer? Computers speak numbers, not language. So at some point, every word has to become a number. The obvious solution, make a list. Cat is 1. Dog is 2. Airplane is 3. King is 4. Queen is 5. Clean and simple, and completely useless. Here's the problem. In that system, the distance between cat and dog is exactly 1. The distance between cat and airplane is also exactly 1. To the computer, they're equally different. But you know that's wrong. Cat and dog share something real. They're both pets. They show up near words like vet, feed, fur. Airplane doesn't show up near any of those. The numbers don't capture that. To the machine, every word is a stranger to every other word. What we actually need is something different. Not a list, a map. A space where similar things sit close together, where the distance between points means something. That's what an embedding is. A map from words into geometry. Here's what's remarkable. You don't design the map. The machine builds it itself. In 2013, a team at Google published a system called Word2Vec. The core idea was almost embarrassingly simple. Take any sentence, cover one word, ask, what fits here? Here's an example. The blank chased the mouse. Cat fits, dog fits, owl maybe. Airplane? No. Train on enough examples, billions of sentences from the internet, and the model starts to learn something subtle. Not definitions, not grammar, but neighborhoods. Which words tend to live near which other words? Here's a way to feel this intuitively. Imagine you wake up in a foreign country with no dictionary. You don't speak a word of the language, but you start listening. And you notice, every time you hear one word, you tend to hear certain others around it. Over weeks, you start to feel which words are related, even without knowing what any of them mean. That's exactly what Word2Vec does. It learns meaning from company. The linguist J.R. Firth put it perfectly back in 1957. You shall know a word by the company it keeps. Word2Vec is that sentence implemented as code. And once it learns those neighborhoods, something unexpected appears. Geometry, not programmed, not designed, just there. Emerging from the patterns, man and woman are separated by a direction. King and queen are separated by the exact same direction. Royalty is another direction. Capital cities are another direction. So if you start at king, move in the direction that takes you from man to woman, you land at queen. King minus man plus woman equals queen. The map didn't just organize words. It found the hidden structure of meaning itself. You might be thinking, okay, interesting trick with language, but how important is this really? More than you might think, because the idea works for anything, not just words. AlphaFold solved protein folding, one of biology's hardest problems. It uses embeddings for amino acids. The sequence of a protein gets mapped into a space where chemical relationships become distances. The geometry reveals the shape. Recommendation systems embed users and movies into the same space. You and a stranger end up near each other, not because someone matched you manually, but because your tastes point in the same direction. Close in space means you'll probably like what they liked. Drug discovery uses embeddings for molecules. Two compounds that sit near each other in embedding space tend to behave similarly in the body. Want to find a new antibiotic? Look for neighbors of the ones that already work. The pattern is always the same. Find a domain. Find its relationships. Build a space where those relationships become geometry. And suddenly, math works on meaning. One more piece because it's important. Early embeddings like word 2, vec, had a limitation. Every word got a single fixed position in space. Bank always lived in one spot. The financial bank, the river bank didn't matter. One word, one point. Context was lost. In 2018, a model called BERT changed that. BERT generates a different vector for the same word depending on the sentence around it. Bank near deposit lands in one region. Bank near river lands somewhere else entirely. Same letters, completely different meaning, completely different position. This is called contextual embedding, and it's what powers the language models you interact with today. Every time the model processes a sentence, every word is being placed and continuously repositioned based on everything around it. The whole network is a machine for turning language into geometry dynamically in real time. So, what is an embedding? It's a translation from the world of symbols, words, molecules, proteins, into a space where mathematics can work on meaning, where similar things are close, where relationships become directions. The reason this matters isn't just technical, it's philosophical. For a long time, people assumed that meaning was too slippery, too human, too complex to formalize, that a computer could manipulate language without ever understanding it. Embeddings don't settle that debate, but they do show something surprising. That meaning has structure, that you can find it, represent it, and do math on it. King minus man plus woman equals queen. Not poetry, math. And the fact that it works at all tells you something profound about the hidden geometry of thought. Is there a topic you'd like me to cover? A paper, an architecture, an area where you think structure is doing the real work? Leave it in the comments. And if this was useful, subscribe and leave a like. It helps more people find this kind of content.